All right, welcome to Math 1200, week one, lesson number one. My name is Professor Lindquist. I hope that you're having a pretty awesome and special day yourself. I'm looking forward to our semester together for a lot of reasons, not the least of which is that I have designed this course. And one of my frustrations, a little bit of background on me, which is what we'll start with. I hated math until 11th grade. I hated it because teachers would come in the room and they would just give me a whole bunch of rules and they would say memorize these rules and do what I say because I am God and you will do what it is that I said. So instead what I did was I just turned it off, and I got great grades in everything. I mean, I didn't get bad grades in math. I got like a 90, but I hated it. I found no enjoyment in it and no use for it, and couldn't understand why I would ever want to study it. And as far as I was concerned, as soon as I could stop taking it, the better. But that all changed. It definitely changed when I hit 11th grade. I'll tell you a little bit more about that in just a couple of minutes. Now, a little bit about me, and a little bit about the course structure and the personality of what we have going on here. First off, I am what a lot of people would consider to be an old school type of leader or instructor. I coached wrestling for 30 years. I coached baseball and softball combined for approximately 40 years. And I am old school. I am here to work. I am here to do the best I can, to teach as best I can, and to get you guys to really love it and to enjoy it and to have a great time with it and to learn from it. Not a cakewalk. Now, as far as what I am here to do personally, well, on my end of things, just outside of the classroom, I love to fly fish. That's this photograph right down here. That's the Delaware River. I taught for all those years, and then my wife and I built the house on the Delaware River where I guide fly fishing now. I also love photography, which is this picture on the lower left. My wife and I raise miniature Australian Shepherds. We really enjoy them. They're a lot of fun for us. And I also write. I write for a lot of magazines. I write for fly fishing magazines like American Fly Fishing, Fly Tire Magazine. I have the most respected magazine in the field is called Gray's Sporting Journal, and they have accepted an article of mine. It's a matter of when they think they can use it in an article before it actually comes out. Now, as far as the course structure goes, it's a pretty straightforward deal. All of my courses run the same way. First off, you're going to get homework virtually every night or every lesson. And when you do the homework, you submit it. And when you submit it, very important, please, no OneDrive assignments. I don't like those at all. It's very annoying to have to open them up and go through. It's a waste of time. Way easier to just do the assignment on a piece of paper, take a picture of it with your cell phone, attach it to an email, send it to me. I'll take a look at it. It goes quick. It goes easy. When I look at your homeworks, what I'm really trying to judge is if there's anything common that the class is missing, that they're not understanding. If everybody in the class is getting number 3 wrong, I obviously didn't do much of a job trying to teach number 3. So I have to go back and hit it again in another way. Though we do hit almost every topic, we spiral. We come back to it 3, 4, 5, 6, 7 times so that everybody in the chance has a chance to learn it. One of my expressions that I really like is, it doesn't matter how fast you learn, it matters that you learn. Okay? Now, going back to when I started to really enjoy mathematics, I was an 11th grade student at Bayport Blue Point High School on Long Island, and I dated a girl named Betty, and I was head over heels for Betty, and she was really good at math. And I said, I got to impress this girl, so I guess I better get good at math too. So that kind of started me caring about my math grade. And then I had an amazing teacher in 12th grade, Mr. Braze. He was just fantastic. And he started to explain math the way this slide does. Mathematics is the science and the study of quality, structure, space, and change. Mathematicians seek out patterns. They formulate new conjectures, and they establish truth by rigorous deduction. from appropriately chosen axioms and definitions. Now, this is really big because it establishes truth. That's huge because in our society today, a lot of people want to deny truth, but math is all about getting to the truth. In other words, math is the rigorous deduction of the world around us using logic and reasoning. At the heart of math is logic and reasoning. And that, folks, is what we're going to do. We're going to learn how to employ logic and some reasoning to the world around us so that the world around us makes a whole lot of sense. We begin to see it that way. But before we get a little more into what math is, let's talk about what it is not so we can get rid of these thoughts right away. Mathematics is not arithmetic. Arithmetic deals only with numbers, things like decimals and fractions. It's a small piece of the mathematics pie. Algebra, probability and statistics, geometry, calculus and trig. We're not going to do any calculus in this course. All of these things are fair game subject matter for the course, and arithmetic is just a little tiny piece of it. In fact, you're going to learn a lot of very surprising things about arithmetic as the semester goes on. At the heartbeat of mathematics is logic and reasoning applied to the world that we perceive daily. Mathematics is money, not just dollar bills and counting money. That's arithmetic. It's money in the sense of understanding how money operates. It's the flight of a ball. It's the fact that your brain on the inside is somehow able to calculate where that ball is going to come down so you can stand underneath it and catch that ball. It's rockets being launched to the moon and figure out, is it going to make it to the moon? There's a lot of mathematics involved in that. In fact, Einstein has a pretty famous quote when he said to someone to not worry about their difficulties with mathematics. He was talking to a math student. He assured them that his difficulties were far greater because Einstein knew that math is, as it says a little later, the arbiter of the sciences. And if the math says it's not true, it's not true. Science isn't the final determiner. Mathematics is. The Iron Dome in Israel, a while back, Iran launched a whole bunch of missiles in one day at Israel. And likewise, Hezbollah and Hamas. But Israel has this thing they call the Iron Dome, which is other missiles that take out the missiles being shot in by them. And the whole thing is a game of math. It's all mathematics, computing it out. One of the greats, one of the great minds of the 20th century is a man named C.S. Lewis. He wrote the Narnia Tales. He was a prolific author, and he was the chair of literature at Oxford University, very prestigious position. And one of the things that made his writing so great, a pillar in the greatness, is that his mom's side of the family were all mathematicians. And what that did was it gave him an ability to use logic and reasoning that the average writer didn't have. And that's one of the things that made his writing so powerful. Now, another guy to think of is Vincent van Gogh. Don McLean, he wrote the song American Pie. You know that song, right? Bye, bye, Miss American Pie. Oh, I should tell you at this point, I was cut from a church choir. Yes, that's how bad a vocalist I am. So, I struggle with it. But I do like Don McLean, and I do sing the song even though I stink at it. On the same album, it's called American Pie, that has the title track. He has another song called Vincent, and it's about Vincent van Gogh, and it begins, Starry, Starry Night. Now, as that song goes through, he gets to the point where he talks about how Vincent tried to say to people through his paintings the world that he saw around him. That is what I am going to try to do in this course, and I hope I'm going to succeed. I've been doing it for years, and it's worked well so far. This course is about perceiving the math around us, chewing on it, digesting it, gaining the mental nutrition it offers, and then, from that perspective, answering the typical math questions on the test. We will learn math through understanding concepts and not as a set of rules just to be understood and blindly followed. I'm going to show you a psalm in a minute. When we get to that psalm, you're going to understand that following the rule is a whole lot more successful if there's understanding. When you understand what it is you're trying to learn, stays in long-term memory. It requires less boring study. Oh my God, I hate studying just for the sake of studying. The concepts transfer, and then you learn how to apply those how to apply the concepts that transferred, and then you have tremendous power of the mind. I love what Galileo says here. Nature is written in a mathematical language. It's all over the place for you to see. When I began to look at math, and this is what Mr. Braves, my 12th grade teacher, taught me, when I began to look at math not as a set of isolated rules, but as a cohesive whole that expresses the intellect behind creation, the mind behind the universe, that explains how all of these things work together. I mean, there's this thing in science called the fundamental entropy, which entropy states that everything tends to a state of disorder. Yet if you look at the world around you, there's order absolutely everywhere. And we're going to get into some of that order in just a second. For example, if you look at itself and the way the planets go around and stars and nebulae and so on go around the universe, you have what we call Fibonacci sequence. But it's not found only there. It's also found in shells and in plants. It's found in the way trees break down with their limbs as they keep going out. It's found in what we recognize as beauty. It's found in the proportions of our body. It's found in DNA. In other words, it is the basic building block of everything around us. Mathematics, at the heart of creation, is this idea of mathematical cohesiveness, mathematics bringing it all together. When I began to look at mathematics as trying to understand the way the world worked, I started looking at mathematics as something pretty cool, powerful. When I looked at mathematics as teacher said so, nah, boring. You're missing the whole point. So we're going to get into the mathematics as we see it in the real world and as it explains the way we understand stuff. Now, you do have to understand, people spend lifetimes trying to get this down pat. So we're not going to cover all of the ways in which this is done, but we're going to cover a lot of them. And we're going to use that as a way to help you understand the mathematics that you're going to learn throughout this year, and hopefully any other course after this. So I talked before about that psalm, and what it says is, teach me, Lord, the way of your decrees. In other words, your rules. But don't just teach me the rule. That's not what it says. It says, don't just teach me the rule. It says, teach me the way that I can follow it. Give me understanding. That's what this course is all about. Giving understanding. When you get that understanding, all of a sudden it's like, wow. It's not just telling me to do a rule for the sake of doing a rule. Like, for instance, when you're a little kid, one of the most famous rules is don't lie, right? It's one of the 10 Commandments. It's kind of everybody in the world knows you're not supposed to lie. And when you're a little kid, the first couple times you lie, you might get away with it and get something selfish for yourself. But then one day, someone lies to you, and you start looking at lying as something very, very different, because you can understand the pain that comes along with the lying. And once you understand that, the whole rule of don't lie takes a whole new meaning in your life. And that's what we're going to do here. We're going to give understanding so that you can follow these rules, so that you can just see what the rules are going to be, because they make sense. Now, there's also a practical end of class, all right? That's the conceptual end of class. The practical end of class involves the praxis test, praxis power. This is going to be a section of each of the days that we teach, or just about every day that we teach. I live by the mantra, performance is a function of preparation. I really do. It's really important to me. Failing, and other people say it this way, failing to prepare is preparing to fail. Performance is a function of preparation. If we prepare properly, we will do well. And many of you are going to have to take the praxis test. And in order to pass that, you're going to have to prepare for that. So a little piece of every lesson that we do throughout the year will prepare you for that test. Now, here's an example of thinking mathematically. Most people don't think mathematically. Here's the rule. Ready? Teacher would walk in and write this on the board. The objective today is to apply that the sum of any two sides of a triangle are greater than the third side. Well, this is kind of common sense, and you've known it since you were a child, a little kid. I'll give you what I mean. Let's say we're going to go from Hackensack, New Jersey, where the school is, down to Freehold, New Jersey, the birthplace and hometown of one Bruce Springsteen, one of the greatest musicians to ever live. I think everybody understands that the quickest way to get from Hackensack to Freehold is a straight line. That's the shortest distance. Any other way to get there is longer or greater. Well, let's say instead of going from Hackensack directly to Freehold, we go from Hackensack to my hometown of Bayport, and then we go from Bayport over to Freehold. Obviously, if I go the Brown way, from Hackensack to Bayport and Bayport to Freehold, that has to be longer than the straight line way. Now notice this is a triangle with two brown sides and a blue side. So the sum of any two sides, the two brown sides, has to be longer than the third side. In other words, there's no way that going from Hackensack to Bayport and then Bayport to Freehold is going to be quicker or shorter than going from Hackensack directly to Freehold. Now, school would say to you, the sum of the lengths of any two sides of a triangle is greater than the length of the third side. And then they start with A plus B is greater than C, A plus C is greater than B, and oh, by the way, B plus C is greater than A. Get a few of these rules in a day, and right about now, the students are doodling in their math books. They're saying, forget this. This is boring. But you've known this since you were a little kid. You've known that to go from one place to another, like Hackensack to Freehold, go there in a straight line. Any other two ways have to be longer. So this says, which of the following cannot be the lengths of the three sides of a triangle? Now I'm going to introduce you to the next premise of our videos. You will notice that our videos do not run for the length of time of the credit hours for a week. And there's a big reason for that. The reason is very simple. During the course of the videos, you're going to be asked to stop and start, which you will do in a minute. And stop and start means stop the video, do the question, start the video. I, on the other hand, will pause a brief amount of time, 5 or 10 seconds, and then I will start answering the question. I'm not going to sit there and keep the video running while I wait for you to do the work, okay? So, which of the following cannot be the lengths of the sides of a triangle? Stop your video now, do the work, and then start your video. Okay, so I assume you have started the video up. Let's go through and see what can and cannot work. 3, 4, 5 does work because 3 plus 4 is 7, that's greater than 5. 4 and 5 are 9, that's greater than 3. And 3 and 5 are 8, that's greater than 4. Any two sides have to be longer than the third, the sum of any two sides. B works because 6 and 7 is 13. 7 and 10 is bigger than 6. 6 and 10 is bigger than 7. We're all good there. 8 and 3 is 11. That's bigger than 8. 8 and 3 is 11. We already said that. That's bigger than 8. And 8 and 8 are 16. That's bigger than 3. That works. But look at this guy. 8 and 7. 15? I don't know about that. Let's let the 15 be from this top point here to the bottom right point. If that's the 15 that runs straight down there, then this guy here is 8 and that's 7. How could the straight distance be 15 and this only be 8 and this only be 7? Because that has to be longer. Because the shortest distance is the direct distance. That can't be a triangle. So D is, or cannot be, the three sides of a triangle. Now, these are kind of topics pulled out random. We're not developing anything here. We'll start doing that a little later in the lesson. But I just want to show you again how thinking mathematically explains a formula. When you're in high school, you probably learned at some point that an inscribed angle is half, the measure of an inscribed angle is half the measure of the intercepted arc. So if this pink arc over here was 100, then the angle would be 50. And if that's the only rule I have to teach you, then this would be really easy and you would never even worry about the concept behind it. But by the end of this chapter that would include this material, there's probably somewhere between 6 or 7 angle rules and another 3 or 4 length of segment rules. So that's a total of 11 rules. And all of a sudden, one turns into 11 and you start getting confused. Okay? Think of phone numbers, right? If you only had to memorize one phone number, you wouldn't forget it. Or locker combinations. But if you have to memorize 11 different locker combinations, this is not so easy. So how can we have a concept behind this that has it all make sense? Well, let's look at this figure on the lower right. You can see that there's a triangle inside the circle. We call it inscribed. And these are all inscribed angles. Angle A, angle B, and angle C. They're all inscribed angles. You'll notice that each one intercepts an arc, like the pink intercepted arc, on the circle. And all 3 arcs that are intercepted make up the whole circle. So there's nothing missing here. And then, of course, the triangles, intercepted angles, are connected to all of the arcs. Well, here's the thing. How many degrees in a circle? If you go all the way around a circle? 360, right? Yeah. Mm-hmm. And how many degrees on the inside of a triangle? The measure of the 3 angles of a triangle? 180? So wait a minute. The 3 inscribed angles cover the whole circle. And the angles only add up to 180, but the circle adds up to 360. Oh, wait a minute. Wait a minute. Those angles have to be half the arcs. Because the angles cover the whole circle. And the angles only add up to 180, but the circle adds up to 360. Here's another one that we can talk about. Ready? The distance formula. Here it is over here on the upper left where it says distance is x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. First off, I never teach it that way. I teach it as the x from the second point minus the x from the first point squared plus the y from the second minus the y from the first squared. And then you start plugging in numbers and working it all out. That can, if you teach it as this isolated rule, you're like, oh my God, oh, it's so complicated. But it's nothing more than the Pythagorean theorem. Look at the problem on the right. We want the distance d from the first point, the x from the first point, comma, the y from the first point, and the x from the second point, comma, the y from the second point. Well, if I drop these perpendiculars and horizontals going down here, I just made a right triangle. And we know in a right triangle that leg squared plus leg squared is equal to hypotenuse squared, or a squared plus b squared is c squared. Or in this case, a would be 1, 2, 3, and it's going to be the difference in the x's, the second x minus the first x, and b would be the second y minus the first y, because that's the vertical height, and we know y is the vertical component. So in other words, the distance formula is nothing more than the Pythagorean theorem formula done on a graph. Students these days learn the Pythagorean theorem in about 7th grade. So if we just taught it to you as a Pythagorean theorem problem, it makes perfect sense. And then if instead of just saying x sub 1 and x sub 2, we said the x from the first point and the x from the second point, then all of a sudden you're like, well, wait a minute, this isn't so complicated. This makes sense. And that is how we want to learn to look at math. Now let's rock your understanding of addition. This is really, when you start talking about understanding math, find the sum of 9 and 5. Well, pretty easy. You think it's 14, right? I don't know about that. It could be 2. Huh? How could 9 plus 5 possibly be 2? Well, what if we're talking about 9 o'clock? Or what if we're talking about clock math? 9 o'clock, adding 5 hours. So if I'm at 9 o'clock and I add 5 hours, I don't end up at 14. Well, maybe in the military time, but I end up at 2. So we have to be careful about what system we're adding in. Now, if I did the same problem about 9 plus 5, and I was using the hexadecimal base system, which we'll talk about in a little bit. Don't let it scare you. Hexa 6, decimal 10, 16 is your base. If we did that, well, then the answer would be E. Huh? What are you talking about? Well, if we take a step back and we begin to understand the basis of number systems. Then all of a sudden, exactly what addition does and does not do and imply begins to make a whole lot of very powerful sense. A lot of computer programs use hexadecimal for programming. All right, so if you plan on studying computer programming in college, you may get into hexadecimal a whole lot. But we'll get more into that a little bit later. Clock math. So we're going to do clock math here, and clock math is always the remainder upon division by 12, because anytime we go past 12, you notice the numbers repeat, right? 12 is like kind of like a 0. It's the starting point. And then 1, 2, 3, 4, all the way around to 12. It doesn't go 13. It goes back to 1, 2, 3. So if I do clock math, it's always what's remains, what's left over after division by 12. So let's do some math problems right here. Let's have you try the first row straight across. Numbers 1, 2, 3, and 4. Stop and start. Go ahead. Okay. Now, number 1, 3 plus 4. Yes, 3 plus 4 is 7, right? You're going to go to 3 and then 4 more. 1, 2, 3, 4. I end up at 7. Beautiful. And 9 plus 3 is going to be 12, right? Well, it's kind of 0 because, remember, it's the remainder upon division by 12. So I do 9 plus 3. There's 9 and 3 more. And yes, I do get up to 12, but in clock math, I want the remainder after division by 12. If you divide 12 by 12, there's no remainder. What about 9 plus 4? Well, you could draw it, right? You could come over here and go 9 and then add 4. 1, 2, 3, 4. It's 1. Or you could say 9 plus 4 is 13. And when I divide 13 by 12, the remainder is 1. What about 5 plus 10? Well, 5 plus 10 is 15, right? And 15 then divided by 12, it goes in once, but I don't really care about that. I care that there's a remainder of 3. So 5 plus 10 in clock math is 3. Okay? Now, what about 8 minus 7? What would that be in clock math? Good. I like it. 1, right? Pretty simple. Now try 8 minus 9. Well, 8 minus 9, start at 8 and go backwards 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 8 minus 9 is 11. Okay? You try the last two. Okay. I was hoping you would just stop and start. Sorry if I didn't mention it. 4 minus 11 is 5. Ready? Here's 4. Let's go backwards 11 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you could also realize that going backwards 11 in a clock where it's a set of 12, you could go forward 1. Okay? And 10 minus 12, what do you think you're going to get there? 10 minus 12 is just 10, right? Because going 12 is just going all the way around the circle. All right. Now you get to do another set. If this is the beauty of a video course, let's just say that you struggled on what we just did. Go back and watch the last 2 minutes, 3 minutes of the lesson. Try to understand a little bit better, and then come back and try these guys. Go ahead, give it a shot. It's stop and start time for you. I'll go over the answers in just a minute. Do all 8 questions. Okay, 3 plus 5, that's 8. But 11 plus 3 is not 14 because there is no 14 o'clock on our clock system. So 11 plus 3 is 2, right? Because 11 plus 3 is 14. When you divide 14 by 12, the remainder is 2. Or you start at 11 and go up 3. 1, 2, 3. 11 plus 8, well, that's 19, but there is no 19. So 19 divided by 12, what's that remainder? It's 7. You could also sketch it out. Here's 11. 1, 2, 3, 4, 5, 7, 8, 9, 10. Oh, I only want to go up 8. Sorry, 8. Up 1, 2, 3, 4, 5, 6, 7, 8. I'm at 7. 9 plus 10, that would be 19. 19 divided by 12 leaves a remainder of what? 7. Same as we did before. Okay, 8 minus 4, 4. I like that. 8 minus 11, well, that's a little tricky, right? Because if I'm at 8 and I go backwards 11, that brings me all the way to 9. What about 4 minus 9? I'm at 4. Whoop. Minus 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 7. And 2 minus 12? Well, as we said before, when you subtract 12, you just end up back where you started. Ready? I'm starting at 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm back at 2. So 2 minus 12 is actually 2. So when we assume that, like all our lives, 2 minus 12 has been negative 10, but that's because we're operating in the, and I quote here, real number system, okay, where we have rational numbers, irrational numbers, and so on. But when I start operating in the clock math number system, or as we mentioned with hexadecimal, or many other systems, the whole thing changes up. Now let's do some multiplication. Basically, you multiply, and then you see what's the remainder upon division by 12. Let's see you try numbers 1 through 4. Just do 1 through 4, stop and start. I'll go over the answers in a minute. Go ahead. Okay, so 3 times 5 is 15. 15 divided by 12 has a remainder of 3. 11 times 3. Well, 11 times 3 is 33. And then 33 divided by 12 would be 24. That's a remainder of 9. So it is equal to 9. Now, how can you do this on your graphing calculator or your calculator? I do like having a graphing calculator, by the way. The way you do it is simple. You just do 33. Then on your calculator, you type in divided by 12, and you're going to get a decimal. Okay? You get like a number and a decimal. In this case, it would be 2.75. So subtract the 2, whatever the whole number is, because that's just how many times you go around the clock. So subtract the 2. So now you're going to get 0.75, and then do times 12. With clock math, you'll always do times 12, and it would come out to be 9. 3 times 8 is 24. If I divide 24 by 12, the remainder is 0. So that doesn't have any remainder, therefore 0 is the answer. 9 times 2 is 18. 18 divided by 12, you get 6 left over. If you did it on your calculator, you would do 9 times 2 is 18, and it would say divide by 12. That's your next step. That's 1.5. Subtract the 1 times by 12. It'll tell you 6. All right, you try numbers 5 through 8. Stop and start, of course. Okay, 8 times 4 is 20. 20 divided by 12 has a remainder of 8. If we did it on our calculator, I would get 20 divided by 12. And then I would take, it would be 1 point, subtract the 1, and then just multiply by 12. 8 times 2 is 16. Subtracting off the 12, what's the remainder left over? It's 4. You could, if you divided it out, it would come out to 1.3 repeating, and then subtract the 1, and then do times 12, and you'll get 4. All right, 4 times 3. Well, that's 12, so when you divide, there's no remainder. And 5 times 3, we said before, was 15. And 15 divided by 12, the remainder is 3. Or take a calculator, 15 divided by 12 is 1.25. Subtract the 1, you're left with 0.25 times that by 12. 3 is the correct answer. Now, your whole life, you've been dealing with base 10. That's what we normally operate with. A base refers to the number of digits, counting numbers, that are available in a numbering scheme. The highest single digit in the base is always 1 less than a base number. That's because you start with 0, okay? So in base 10, the digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So what would those digits be in base 5? Well, they would be 0, 1, 2, 3, and 4, right? Because your highest one is always one less. It's always one less because you start with 0. What about base 3? Well, that'd be 0, 1, and 2. And what about base 14? Well, that means I have to have 14 different numbers and I start with 0. So the first bunch of them is 0 through 9. But then I get A, B, C, and D. Okay? A is like 10, B is like 11, C is like 12, and D is like 13. Okay? Don't know why we skipped ahead to that one or what happened right there. Now, here's how base 10 works. Okay? Whenever I have base 10 or any base, the ones always go first. Then you get the tens and then you get the hundreds. Now, where does that come from? Well, the ones come from the fact that this is 10 to the 0 power. Then it's 10 to the 1 power. And then it's 10 to the second power. Whatever the base is, okay, look underneath the blue diagram there. Whatever the base is, you always on the right-hand corner begin with base to the 0, then working our way left, base to the 1, base to the 2, and so on. Since we're dealing with base 10, which is what we're so familiar with, we go 10 to the 0, 10 to the 1, 10 to the 2. Now, anything to the 0 power is 1, and there's a 2 in that place, so it means 2 times 1. In the middle column, 10 to the first power is 10. There's a 4 there, so it's 4 times 10, which is 40. If we add that to the 2 ones, we have 42 so far. But then there's 7 hundreds, and we say that because 10 squared is 100. So then the whole thing is read 742. So that's the structure of our number system. And if we don't understand that structure, then we might not understand why we do some of the things that we do. Okay? So here's one where it asks us to convert 101 in base 2 to base 10. Converting 101 in base 2 to base 10. Well, if I do that, remember, we always start with the 0 power on the right. So 2 to the 0, then 2 to the 1, then 2 to the 2. So 2 to the 0 is 1, and I have 1, 1, so that's 1. 2 to the 1 is 2, but I have 0 of them, so that's 0. And 2 to the 2 is 4, right? 2 squared is 4, and 1 times 4 is 4. So then to add up the value, I would get 4 plus 0 plus 1, and that all adds up to 5. What about if we want to convert what looks like 1,001 in base 2 to base 10? So again, starting 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. If there was another column, 2 to the 4, and so on. 1001 means there's one of those 2 to the 1s. Or 2 to the 0, sorry. 2 to the 0 is 1, so if I have 1, 1, it's 1. I have no 2 to the 1s, so I got nothing there. I have no 2 to the 2s, so I got nothing there. 2 to the third is 8. I have one of those, so I have 8. So then I add them all up. 8 plus 0 plus 0 plus 1 is 9. Oh boy, what about 1101, base 2? You notice how I write that little base 2 down at the bottom right there? Okay, that's how we denote that. So there it is, 1101, and then working backwards, that's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on, all the way out to 2 to the 6. Now, if I have 1, 2 to the 0, 2 to the 0 is equal to 1. So I have 1, 1, so it's 1. I have 1 of 2 to the 1s. Well, that's 1 times 2, which is 2. I don't have any of the next guys, but then I have 2 to the thirds. I got one of those, so that's an 8. I have 0, 2 to the fourths. Now, a 2 to the fourth is worth 16, right? 2 times 2 times 2 times 2. I don't have any of those. 2 to the fifth is worth 32, right? Because 2 to the fifth means 2 times 2 times 2 times 2 times 2. A total of 5 2s, multiplying them out. That's 32, right? Because 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 more. The fifth one is 32. So there's 132, so I list that there. And then 2 to the sixth would be 2 times 2 times 2 times 2 times 2. And another 2, boy, I'm going backwards there. I don't know what's up with that. That would be 64, and I have one of those. So I have 164, I have 132. I don't have any 16s. I have 1 8. I don't have any 4s. I have 1 2, and I have 1 1. Adding them all up, that's 96, 104, 106, 107. So in base 2, that looks like all these numbers on the top. It looks like 101. But in base 2, that's just 5. 1001 in base 2, well, that's just 9 in base 10. And this is 1,101,011, looks like, but it's base 2. It's 1101011, and that's really just 107. So that leads us to the old joke. There are only 10 kinds of people in the world. Those who understand binary and those who don't. Ha 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 ha. You get it? 10 kinds of people in the world. 10, 1, 0. So 2 to the 0, 2 to the 1. If I have no 2 to the zeros, 2 to 0 is 1. I don't have anything there. 2 to the 1 is 2, and there's one of those. So that is a way of saying there are 2 kinds of people in the world. Again, if this gives you difficulty because it's the first time you've seen it, go back and watch this section of the video over. Okay. Now let's compare base 10 to base 16. Let's find some equivalent numbers. Now, base 16 is hexadecimal. And remember, this is used a lot for computer programming. So is binary, by the way. There used to be this computer language called assembly language programming. For all I know, they still use it. And everything was either yes or no, yes or no, yes or no. That's 0, 1, 0, 1, 0, 1. Everything would work like that. But I think we're going to work on that in just a few minutes. So it says convert 1A5 to in base 16 to base 10. 1A5. So see if you can figure out how to do that. Remember, we start on the right-hand edge with 16 to the 0, then the next column over 16 to the 1, and so on. Stop and start. Only that first question. Okay. So, again, right, 16 to the 0. We start on the right-hand edge. 16 to the 1, 16 to the 2. So there's 5 of these guys. A of those guys. Now, remember, A is really 10, right? Got that up top here because 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. And then 1 here for 16 squared. 16 to the 0 is 1, and 5 times 1 is 5. 16 to the 1 is 16. 10 times 16 is 160. And then 16 squared is 256, and there's one of those. So if I add that all up, I get 421. Okay. Right, 256 plus 160 plus 5. You can see a little order of operations working there, and why it should. Okay, try the next one. 342b, 16. Convert that to base 10. Again. Stop and start. Okay. So 16 to the 0, 16 to the 1, 16 to the 2, 16 to the 3. You see how those exponents are increasing to the left? 0, 1, 2, 3, and the base stays the same, 16 all the time. So B is really 11. So 16 to the 0 is 1. B times 1, or 11 times 1 is 11. So then we got times 16 squared, which is 256, times 16 cubed, which is 496. They'll just keep working our way out. 16 to the 1, and there's a 2 on top. So that's 2 times 16, or 32. So 4 on top here, right? Because that's the number 342. So that's 4 times 16 squared, which is 4 times 256, which is 1,024. And then 3, 16 to the third power. 16 to the third is 4096. I have 3 of those, so 3 times that's 12,288. And then I add them up. 12,288 plus 1,024 plus 32 plus 11 is 13,355. Now let's have you add up. It's a little tricky. It's going to require some thinking on your part. A5 base 16 and C41 base 16. Have fun. Enjoy. We'll see how you do with this. Believe me, this is not the only time you're going to see this. You're going to see this multiple days in a row so that you can understand and get it down pat. Okay? Go ahead. Okay, time for me to start up my end of the deal. A5 in base 16. Remember, 16 to the 0, 16 to the 1. 5, right? Because 16 to the 0 is 1s. And then 16 to the first is 16. And A is equal to 10, right? 8, 9A. So that's 10 times 16, which is 160 plus 5, which is 165. Now, C4, 1 to the base 16 will have 16 to the 0, 16 to the 1, 16 to the 2. There they are. I have one of those, so that's 1. I have 4 of those, so that's 4 times 16 or 64. And then I have C of those. What is C? Well, 8, 9, 10, 11, 12. C is 12. So that's 12 times 16 squared is 256. That all adds up to 3,137. As always, if you struggled with this, go back and watch this over again, right? Performance is a function of preparation. That's a lot of good preparation on your part if you do it. So here's a quick video on binary numbers being explained.
Modern-day computers use electricity to work, and inside of a microchip, electricity is turned either on or off, which is represented by the symbols 1 and 0. This is called binary. You've probably heard of binary already, and that's how computers work. But do you know how binary works? Well, you're about to find out. But first, we need to understand exactly how our numerical-based system, known as decimal or base 10, works the way it does. So, there are 10, count them, 10 symbols that we use for all of our numbers. Starting from 0, we can count all the way up to 9 before we run out of symbols to use. Now, we could just keep adding symbols at this point, but that would get out of hand very quickly. I mean, can you imagine having to memorize a specific symbol for every single number? That's ridiculous. And that's why we reuse the same symbols over and over again in a very clever system called positional notation. So, in the base 10 system, as soon as we get to 10, or an exponent of 10, we need to add another digit to the left of our current digit. Because there are 10 symbols, each new digit has to have a value 10 times greater than the digit to its right. So that's using 10 symbols. But what if you had only 2 symbols to work with? Well, then everything that I said still applies. With just 2 symbols, each new digit needs to have a value 2 times greater than the digit to its right. So a sequence like this would equal 1 times 128, plus 1 times 16, plus 1 times 8, plus 1 times 2, plus 1, which is 155. And that's how you count in binary. It's actually really simple. It's just multiplication and addition. Now, it gets a lot more complicated from here, with bits and bytes and Boolean logic and ASCII, and the list just goes on and on. So let's return to base systems. There are a lot of ways to write numbers other than decimal and binary. You've got base 2, base 3, base 4, base 5, I could go on. They all work with the same principles of positional notation. So you might be wondering, with all these numbering systems to choose from, why do we use base 10? That's a good question. This goes all the way back to Roman numerals and Egyptian hieroglyphs. It's likely that we use base 10 simply because we have 10 fingers, also known as digits. Other base systems like base 8 and base 12 are actually superior for simple everyday math, since 8 and 12 are much more easily divisible than 10. But it's definitely too late to change our minds about using base 10. We'll probably be stuck with it forever. Switching away from it now would be even harder than trying to convince America to drop the imperial system and finally switch to metric. You know, like the rest of the civilized world. Like, yeah, the metric system is superior, but who's gonna tell America what to do? Now, if you're going to be using base 12 or any other base system with more than 10 digits, it's standard to use letters to represent numerals higher than 9. So 10 is A, 11 is B, 12 is C, and so on. This is called alphanumeric. You know those URL shorteners that you see on Twitter and elsewhere? Have you ever wondered how they work? All those jumbled characters really just represent a very large number. By using numerals and every letter of the alphabet, you can get all the way up to base 36. Using lowercase and uppercase letters gives you base 62. And with that, you can get all the way up to 14 million with only 4 digits. With just 10 digits, you can get up to 839 quadrillion possible values. That's a lot of shortened URLs. So, you just learned about positional notation, binary numbers, numeral-based systems, alphanumeric characters, and URL shorteners. I hope you enjoyed it, and if you're in the mood for more learning, maybe you'll like today's video sponsor, which is the excellent lynda.com. For the past 6 years, I have been using and recommending lynda.com to people as an excellent means of learning new things, especially software. You see, over 6 years ago, I wanted to learn how to use
so
Photoshop.
we got our
so
point
I Googled
about
around,
all the
and as
number
usual, many
systems,
of the
and I did
software
use
tutorials
lynda.com
I
for a
found
long
just
time.
assume modern-day computers use
All right, so let's do some base 5 questions. I want you to try numbers 1, 2, and 3. Try them all. Remember, it's the remainder upon division by 5, and I will give you the correct answers after a stop and start. Okay, 1 plus 2 is 3. Makes perfect sense. 1 plus 4 is not 5, because in base 5, the highest number is 4. So it's 0. And 4 plus 4 would normally be 8, but the remainder upon division by 5 is 3, because there is no 8 in base 5. Let's review the lesson now. Ready? You're going to answer these 5 questions. Answer them, and then I will come back, give you the correct answers. So this is a stop and start, and it will take a little while. Go ahead. Okay, so converting 1, 1, 1, 1. Remember, we have 2 to the 0, 2 to the 1. It's always the base working backwards, multiplying by 1 more 2 each time. So I have 15, right? Because I have 1, 8. I have 1, 4, 1, 2, and 1, 1. Adding that all up, I get 15. What about 5D in base 16? Well, this is 16 to the 1 and 16 to the 0. 5 times 16 is 80. And then D, which is really 13, right? Because A is 10, B is 11, C is 12, and D is 13, times 1. And 80 and 13 make 93. Find the following sum of binary numbers and express in base 10. That looks like 110 plus 11, but we're doing binary. So adding them up, that's 110, which works out to be 6, right? Because I have 0 of these, 1 of those, which is a 2, and 1 of those 4s, so that's altogether 6. And then 1, 1, which would be a 2 and a 1, which is 3, and 6 and 3 make 9. Find the product in base 7. Well, 5 times 4 is equal to 20. The remainder upon division by 7 is 6. And 3 times 4 is 12. The remainder upon division by 6 is 7, base 7 is 0. Okay. 33 base 8 minus 14 in base 8. This is a little tricky. Okay, so 33, I can't do 3 minus 4, so I put a 1 up there just like we normally would. However, here's the tricky part. Ready? That 1 means 8. Let me say that again. The 1 is really an 8 because I'm borrowing one of the value of this next column over. And each place out is another 8. So that's 8 and 3 make 11. 11 minus 4 is 7. And then 2 minus 1 is 1. If you want to work it backwards, you can just check yourself by doing 17 plus 14 is 33. 7 plus 4 is 11. But 11 in base 8 is really 3. And you've got to include a 1 here, right? Because we're regrouping it. So 1 and 1 make 2, and another 1 makes 3. So it does check back. Okay, let's have you try these 5. Again, stop and start. Really getting a chance to reinforce what we've done today. Just putting it up there for you to follow yourself. Okay. So 3b, right? B is equal to 11. So there's 111. 3 16, so that's 48. And 3 256s. All adds up to 827. Find the sum of these numbers expressed in base 10, 1101. There we have it, right? A 2 to the third, a 2 to the second, no 2 to the first, and 1 2 to the 0. Adding them up, I get 13. 1 0 1 would be 1 2 squared, which is 1 4. No 2's, 1 1. That's 5. Adding up 5 and 13, I get 18 in base 10. Find the product in base 9. Well, 20 divided by 9, the remainder is 2, right? Because 9 times 2 is 18. 3 times 4 is equal to 12, so the remainder is 3. So 3 times 4 is 3. Subtract 33 base 5 minus 14 base 5. 3 minus 4 in base 5 is going to be 8, right? Because when we borrow 1, that's equal to a 5, and 5 and 3 make 8. 8 minus 4 is 4. And then 2 minus 1 is 1, so it's 14. Or it looks like a 14. Perceiving and understanding math behind the rules. Here we go. Good talk here. What we're getting at.
I love mathematics. Is exactly what to say at a party if you want to spend the next couple of hours sipping your drink alone in the least cool corner of the room. And that's because when it comes to this subject, all the numbers, formulas, symbols, and calculations, the vast majority of us are outsiders. And that includes me. That's why today I want to share with you an outsider's perspective of mathematics, what I understand of it from someone who's always struggled with the subject. And what I've discovered, as someone who went from being an outsider to making maths my career, is that surprisingly, we are all deep down born to be mathematicians. But back to me being an outsider, I know what you're thinking. Wait a second, Eddie. What would you know? You're a maths teacher, you went to a selective school, you wear glasses, and you're Asian. Now, firstly, that's racist. Secondly, that's wrong. When I was at school, my favorite subjects were English and history. And this caused a lot of angst for me as a teenager because my high school truly honored mathematics. Your status in the school pretty much correlated with which mathematics class you ranked in. There were 8 classes, so if you were in Maths 4, that made you just about average. If you were in Maths 1, you were like royalty. Each year, our school entered the prestigious Australian mathematics competition and would print out a list of everyone in the school in order of our scores. Students who received prizes and high distinctions were pinned up at the start of a long corridor, far, far away from the dark and shameful place where my name appeared. Maths is not really my thing. Stories, characters, narratives, this is where I was at home. And that's why I raised my sails and set course to become an English and history teacher. But a chance encounter at Sydney University altered my life forever. I was in line to enroll at the Faculty of Education when I started a conversation with one of its professors. He noticed that while my academic life had been dominated by humanities, I had actually attempted some high-level maths at school. And what he saw was not that I had a problem with maths, but that I had persevered with maths. And he knew something I didn't, that there was a critical shortage of mathematics educators in Australian schools, a shortage that remains to this day. So he encouraged me to change my teaching area to mathematics. Now for me, becoming a teacher wasn't about my love for a particular subject. It was about having a personal impact on the lives of young people. I'd seen firsthand at school what a lasting and positive difference a great teacher can make. I wanted to do that for someone, and it didn't matter to me what subject I did it in. If there was an acute need in mathematics, then it made sense for me to go there. As I studied my degree, though, I discovered that mathematics was a very different subject to what I'd originally thought. I'd made the same mistake about mathematics that I'd made earlier in my life about music. Like a good migrant child, I dutifully learned to play the piano when I was young. My weekends were filled with endlessly repeating scales and memorizing every note in the piece spring and winter. I lasted 2 years before my career was abruptly ended when my teacher told my parents, his fingers are too short. I will not teach him anymore. At 7 years old, I thought of music like torture. It was a dry, solitary, joyless exercise that I only engaged with because someone else forced me to. It took me 11 years to emerge from that sad place. In year 12, I picked up a steel string acoustic guitar for the first time. I wanted to play it for church, and there was also a girl I was fairly keen on impressing, so I convinced my brother to teach me a few chords. And slowly, but surely, my mind changed. I was engaged in a creative process. I was making music, and I was hooked. I started playing in a band, and I felt the delight of rhythm pulsing through my body as we brought our sounds together. I'd been surrounded by a musical ocean my entire life, and for the first time, I realized I could swim in it. I went through an almost identical experience when it came to mathematics. I used to believe that maths was about rote learning inscrutable formulas to solve abstract problems that didn't mean anything to me. But at university, I began to see that mathematics is immensely practical and even beautiful. That it's not just about finding answers, but also about learning to ask the right questions. And that mathematics isn't about mindlessly crunching numbers, but rather about forming new ways to see problems so we can solve them by combining insight with imagination. It gradually dawned on me that mathematics is a sense. Mathematics is a sense just like sight and touch. It's a sense that allows us to perceive realities which would be otherwise intangible to us. You know, we talk about a sense of humor and a sense of rhythm. Mathematics is our sense for patterns, relationships, and logical connections. It's a whole new way to see the world. Now, I want to show you a mathematical reality that I guarantee you've seen before, but perhaps never really perceived. It's been hidden in plain sight your entire life. This is a river delta. It's a beautiful piece of geometry. Now, when we hear the word geometry, most of us think of triangles and circles. But geometry is the mathematics of all shapes. And this meeting of land and sea has created shapes with an undeniable pattern. It has a mathematically recursive structure. Every part of the river delta, with its twists and turns, is a micro version of the greater whole. So I want you to see the mathematics in this. But that's not all. I want you to compare this river delta with this amazing tree. It's a wonder in itself, but focus with me on the similarities between this and the river. What I want to know is why on earth should these shapes look so remarkably alike? Why should they have anything in common? Things get even more perplexing when you realize it's not just water systems and plants that do this. If you keep your eyes open, you'll see these same shapes are everywhere. Lightning bolts disappear so quickly that we seldom have the opportunity to ponder their geometry. But their shape is so unmistakable and so similar to what we've just seen that one can't help but be suspicious. And then there's the fact that every single person in this room is filled with these shapes too. Every cubic centimeter of your body is packed with blood vessels that trace out this same pattern. There's a mathematical reality woven into the fabric of the universe that you share with winding rivers, towering trees, and raging storms. These shapes are examples of what we call fractals as mathematicians. Fractals get their name from the same place as fractions and fractures. It's a reference to the broken and shattered shapes we find around us in nature. Now, once you have a sense for fractals, you really do start to see them everywhere. A head of broccoli, the leaves of a fern, even clouds in the sky. Like the other senses, our mathematical sense can be refined with practice. It's just like developing perfect pitch or a taste for wines. You can learn to perceive the mathematics around you with time and the right guidance. Naturally, some people are born with sharper senses than the rest of us. Others are born with impairment. As you can see, I drew a short straw in the genetic lottery when it came to my eyesight. Without my glasses, everything is a blur. I've wrestled with this sense my entire life. But I would never dream of saying, well, seeing has always been a struggle for me. I guess I'm just not a seeing kind of person. Yet, I meet people every day who feel it quite natural to say exactly that about mathematics. Now, I'm convinced we close ourselves off from a huge part of the human experience if we do this, because all human beings are wired to see patterns. We live in a patterned universe, a cosmos. That's what cosmos means, orderly and patterned, as opposed to chaos, which means disorderly and random. It isn't just seeing patterns that humans are so good at. We love making patterns too. And the people who do this well have a special name. We call them artists. Musicians, sculptors, painters, cinematographers, they're all pattern creators. Music was once described as the joy that people feel when they are counting but don't know it. Some of the most striking examples of mathematical patterns are in Islamic art and design. An aversion to depicting humans and animals led to a rich history of intricate tile arrangements and geometric forms. And the aesthetic side of mathematical patterns like these brings us back to nature itself. For instance, flowers are a universal symbol of beauty. Every culture around the planet and throughout history has regarded them as objects of wonder. And one aspect of their beauty is that they exhibit a special kind of symmetry. Flowers grow organically from a center that expands outwards in the shape of a spiral. And this creates what we call rotational symmetry. You can spin a flower around and around, and it still looks basically the same. But not all spirals are created equal. It all depends on the angle of rotation that goes into creating the spiral. For instance, if we build a spiral from an angle of 90 degrees, we get a cross that is neither beautiful nor efficient. Huge parts of the flower's area are wasted and don't produce seeds. Using an angle of 62 degrees is better and produces a nice circular shape, like what we usually associate with flowers. But it's still not great. There's still large parts of the area that are a poor use of resources for the flower. However, if we use 137.5 degrees, we get this beautiful pattern. It's astonishing. And it is exactly the kind of pattern used by that most majestic of flowers, the sunflower. Now, 137.5 degrees might seem pretty random, but it actually emerges out of a special number that we call the golden ratio. And the golden ratio is a mathematical reality that, like fractals, you can find everywhere, from the phalanges of your fingers to the pillars of the Parthenon. And that's why, even at a party of 5,000 people, I'm proud to declare I love mathematics.
All right, so I love mathematics, and I hope that you're starting to see that there's a little more going on here than you ever looked at before. It is to be perceived in all the world around you, and that is exactly what we're going to do this semester. And along the way, you're going to learn how to excel in the classroom or improve in the classroom as never before. I want to focus, speaking of the classroom, on some things you can do to make sure that you succeed in class. First, you want to do all, notice they're capital, homeworks when due. If you do them all on time, you get 10%. If they're late, you lose half credit. So you want to make sure you get them all in on time. It's kind of like getting extra credit. It's the only way you'll come close to extra credit, because you will not get any other extra credit. How you go about your business is critical. You got to have grit. You got to work through it. You got to find ways to make success happen. And it starts with doing your work every single day. Pay attention to due dates on Moodle. It's so important. Every year I get certain kids that will just miss an assignment. And if you miss an assignment, you get zeros. That's really going to hurt your grade. When you guys have projects, work together on them. Take pride in your work. Feel free to spend as long as it takes for you to master those questions. Of course, you're going to submit the work in your own words with your own handwriting and so on, or computer work. But I definitely, look, if I see two things that are word for word the same, I'll just give both people half credit. But I want you to work together to understand the material. All right, we are looking good. That is the end of the first lesson.